Hello, welcome to this lecture on exact and approximate inference. So the reason why this is an online lecture is because I'm not going to be here this week, so there isn't going to be a lecture in person on Monday, but instead we will have this lecture online, which will just be a recorded video. Your tutorial is made available for the whole week, so you can still, so things will go, despite us not having a lecture, in-person lecture, we will have this online lecture, so things will still go as planned. You will still have something to do for this week. Okay, so this lecture is on exact and approximate inference. Now, this is the part of the class where I'll ask you, does anyone know what exact inference is and what approximate inference is? And then one of you will raise your hand, and then maybe you'll say, inference is when we have to actually compute probabilistic queries. And I'll say, yes, that's correct. So when we compute probabilistic queries, we can either do this in an exact way to get the exact solution that we want, which is the actual value for the query. So for example, the probability of x and y given z, where z is some evidence, will equal to 0.8. Okay, so this is for specific values of x and y and z. So maybe the evidence for z is 0, and then I'm trying to calculate the posterior probability of x and y, and I get an actual value. This is a probability. This is a value that's between 0 and 1. So if this is my value v, then v is indeed a probability, so it must fall between 0 and 1. Okay, yeah, all right, that's good. So that's good, right? So notice also that this word inference is here, right? So normally on the lecture slides I had representation because all of the lecture slides before this point was representation, but now we're changing it. We're going to inference. So inference is now calculating these probabilistic queries. So we'll look at two lectures on this. The one lecture, which is this one, will be on exact and approximate inference, and the next lecture will be on what we call particle-based inference, which is an approximate inference type. And you'll learn all about inference in these two lectures, and then we'll move on to something else after that. Yeah, so let's continue. So this is all in the realm of explainable AI, having inference procedures where you actually know how the inference is calculated. So let's now discuss this a bit more in detail. So we must discuss the problem of inference. So this is the problem of inference. And the problem, I always start my lectures with the problem statement. So we're going to discuss the problem of inference with respect to a problem statement. So what is the problem statement? So we need to basically solve this equation. We need to calculate the probability of a subset of variables from our graphical model. So you can think of our graphical model as being something like this. Maybe there's lots of variables in here, and I want to now calculate what is the probability, posterior probability of these two variables, let's say, given some evidence. So maybe I've got an evidence value here h, an evidence value here I. I need to incorporate that evidence in order to be able to calculate the posterior probability over these particular subset of variables. So how do we do that normally? So the problem of inference is that you want to calculate this. So what we then do is we say, well, what is the probability of all of the variables given the evidence that you have? So this is the evidence, and this y is all of the variables that you want to calculate it over, and then you divide it by the evidence, the probability of the evidence. In order to calculate the probability of the subset y and the evidence, you need to then sum over all of the nuisance variables that are in your network. So you're summing over w, where w is all of the nuisance variables. And so this, you can think of this as your full joint distribution, right? This is your full joint distribution. This is the probability of the entire network, right? Where y, even the subset and the nuisance variables are w. So this is the nuisance variable, this is w, this is also w, and so on. So that you have to sum over the y's, which is the subset of the evidence variables, all of the evidence, right? So the y, all of the evidence, and all of the other variables in the network as well. Okay. And then similarly, for the evidence, in order to compute this bottom part here, you need to also compute, we need to compute the probability of y as well as w in order to get, and so it's a joint of everything again, but this time we're summing over y and w. So we're trying to eliminate y, we're trying to eliminate w so that we can get this P of E. So this is basically what the inference problem is trying to do. And the effectiveness of inference in a graphical model, it heavily depends on the network structure. Depending on how these arrows are manifesting in between these variables, then we'll get different kinds of computational complexity or effectiveness for the inference procedure that we're using. So this is the problem. This is the problem of inference. So now how do we actually solve this problem? And there are different approaches of solving this problem, but from a very naive perspective, it looks like this is a very easy problem to solve. Okay, because we're just calculating these different probabilities, so solving it should be extremely easy, right? We just have to marginalize over all of the nuisance variables, which is this W, and then just divide it by the evidence. So you marginalize first by all of the nuisance variables W, and then you marginalize again over all of the Y's to get the top term and the bottom term. You divide them, and then you're done. So let's have a look at this actually in practice. So looking at this in practice, if I got a factor here with the scope of Y, E, so the scope here is Y, it's E, and it's W, then I can have a factor like this. So the probability of Y1, E1, and W1 is 0.18, okay, and so on. And so all of this must add to 1. So what do I do then do? If I go back to this, I have to then sum over. I have to do the stop part here. I need to sum over all of the nuisance variables. So I need to get rid of W, so I'm summing over W. And if I sum over W, I just use the procedures of factors that I've showed you before, so summations and so forth, and then I'll get rid of W. Notice that we still have a probability distribution, and this is now the probability of the thing we're trying to predict and the evidence. So this is now both of them. So that's great. That's the numerator. Well done. I've got the numerator. What about the denominator? Well, it was one step away. I need to get rid of Y as well. So I get rid of Y by summing out over Y. So this is exactly the same as before, but summing out over Y, and then I'll get the probability of the evidence. So then this becomes my numerator. This becomes my denominator. So that comes on the top. This thing comes at the bottom. So if I want to calculate the probability of Y1 given E1, then that is equal to the probability of Y1 and E1, which is this one over here, which is 0.27, divided by the probability of the evidence, which is E1, which is 0.57, and I put this number here at the top, and I put this number here at the bottom. I divide them up, and I get 0.47, and that becomes the posterior probability of Y1 given the evidence of E1. Notice that there is a difference between this here, and there is a difference between what we just computed, which is given the evidence, and the joint distribution of Y1 and the evidence. So there is a difference there. This one here is the stop value here, 0.27. And this one, given the evidence, is this one here, 0.47. So these probabilities are not the same thing. So what is the approach to inference here? It looks really easy when I showed it to you this way, but it is really infeasible. And why is it infeasible? It is infeasible because these tables, if for me to calculate this table, this very first table here, I need to be able to compute the joint factorization of all of the variables in my network. Here I just have 3 variables in my network. There's X. There's X, actually this is not the structure, there's an X, there's a Y, and there's a W, okay? There's a X, Y, and W, so maybe the structure is like this. So you got W here, X here, and a Y here, and it's actually E, so Y, E, and W. So W, and then I need to make it this in E, okay? And then there's a Y, okay? So let me redraw that for you so you don't get confused. So that's going to be that Y, maybe this is the Y, maybe this is the E, and then this is the W. Okay, so then this is, if I have to then create a table, I'll get something like this. Okay, so this is now this is the joint for all of the variables. Okay, good. So if I have more variables here, if I have an A here and a B here and a J here and so on, even if they're binary random variables, this table is going to blow up. It's going to be just for 2, 2, 2, 2, 2, 2. That's 1, 2, 3, 4, 5, 6, 7. It's going to be 2 to the power of 7. If I have 16 variables, this table is going to be 2 to the power of 16. If I've got 100 variables, this is intractable. And so doing it this way is not a good idea. So there's an exponential blow up in the joint distribution. So this is part of the problem statement. So we need better ways of doing it. But it turns out that and these have been proven as in theorems as part of the graphical models inference problem, that exact inference in graphical models is NP hard, which means that we are unlikely to find any efficient solution for exact inference, getting the exact value. And to make matters worse, this is also true for approximate inference. So the approximate inference algorithms are also NP hard. So the good news, so this is the good news. The good news is that these are the worst case results for exact and approximate inference, and most of the time, depending on the structure, inference is generally manageable. But I say depending on the structure, but even with very complicated structures, we can still have manageable inference. So, and we'll see why there are some really good algorithms, and I'm going to show you on how to do inference efficiently for these type of problems. So that's the problem statement, and now we need a solution. So this is the part of the class when I'll be asking you to raise your hand if anybody has better solutions to be able to perform inference in a graphical model. And maybe some of you won't have any good ideas, or maybe some of you will have some good ideas, but it turns out that there's a really good idea, and it takes advantage of the fact that so this really good idea takes advantage of the fact that we can actually manipulate the joint distribution. So if you remember before, I told you that if you have a very complicated Bayesian network, something like this, then you can write out the joint distribution A, B, C, and D as a product of factors. So you can have P of A, and that's P of B, given A, and blah, blah, blah. And you can actually do that for all of them. And we also, the good idea also takes advantage of the fact that each of these particular factors, or these local probability distributions from the second lecture, they are made up of a specific scope. So here the scope is just A, here the scope is B and A, another scope might be C and B, and so on and so on. So these are the two things we're going to take advantage of. So the algorithm is called variable elimination. Variable elimination, it's an algorithm, and it's very much at the heart of exact inference, and it's also at the heart of approximate inference. So variable elimination is the method of choice for inference in graphical models. This is true because you can do exact inference with variable elimination. I'll show you how to do that later on. But also approximate inference, where you're trying to get a value within some error estimate, you can actually still get all of the advantages of the variable elimination algorithm and the things that it exploits. So what are the properties that it does exploit? Well, the first one is that you can sum out over these factors. So for example, P, the joint distribution of A and B, you can actually sum out B to get A. Okay, so in other words, this B here, once you sum out B, it removes it from the factor, and it then becomes P of A. So that's the one important property that we're taking advantage of. And the other one is the property of the joint distribution that we're taking advantage of is the fact that when you have a situation like this, P of A and then P of BC, you can actually, because we're summing over C here, P of A has nothing to do with C because there's no C in this, there's no scope. The scope doesn't involve C, so we can remove P of A from the factor entirely. And so we can take out P of A from the summation, and the summation can continue without P of A because the summation has nothing to do with P of A. Okay, so that's pretty important. Let's actually perform this algorithm and this variable elimination algorithm for you to see how it works on this new graphical model. So this is a new graphical model. It now incorporates a few other things like coherence, whether you're happy with your job, and other things like the job and so on. So we've got the APS and everything else. This is the network we know from previously, but now we've got the three extra things just so we can see how we can perform variable elimination on very complicated graph structures. Okay, so let's see. So suppose that you want to calculate the probability of J. So if you go back to the slide here, that's the probability of the job. Okay, so we want to calculate the probability of J on the extended student network. That's the extended student network is the one I showed you on the previous slide. And we know already that we can represent the joint distribution using the chain rule for Bayesian networks, not the chain rule for probabilities, the chain rule for Bayesian networks. Okay, so the chain rule for Bayesian networks simply means that we're going to say things like, what is the probability of difficulty given coherence, which is this one here? What is the probability of coherence, which is here? What is the probability of intelligence, which is here? The probability of the APS given the intelligence, the probability of the grade given the intelligence and the difficulty, the probability of happiness given the grade and the job, the probability of the job given the APS and the letter, and so on, and the probability of the letter given the grade, and dot, dot, dot. So all of these, we put them all together, and we come up with this. So this is the joint probability of all of these variables for each of those factors that I've shown you. And I told you in the previous lecture that sometimes it's useful to think of these factors, think of these probabilities as factors, right? So instead of representing, for example, P of D given C, this one here, we just represent it as a joint scope. So it becomes D and C, or C and D. Okay, the order doesn't matter. And this is useful because now we can eliminate this entire, all of these givens, and just see things as factors, as tables, as small tables. And so we end up with this. So this becomes now the factor for C is this one here, the factor for DC is this one here, the factor for PI is this one here, and so on for all of these different factors. And so we end up with this joint factorization for the joint distribution. Okay, so the other thing that variable elimination relies on is this notion of a elimination ordering. So let's pick an elimination ordering C, D, I, H, G, A, L. Okay, so this is an ordering in which we are going to eliminate variables from respective scopes. And I'll show you exactly how we're going to do that now. But we need the ordering because we need an instruction of how to eliminate variables. So and the ordering turns out to be a very important and a very crucial element to the variable elimination procedure. So let's look at that. So to calculate the probability of J, we need to sum out all of the variables excluding J for the joint factorization of the joint distribution. So that gives us, so remember this ordering I told you is important, so we're going to actually put the ordering down here, and we need to make sure that when we are doing the variable elimination algorithm that we eliminate the variables in the correct order. So let's do that. So let's push the summation in. So for this summation here, we can push it in according to the ordering. So we're going to push the C the most in because that's what we're going to eliminate first. So let's push the C in first. So it becomes the C goes right to the end, and all of the factors in this block, in this factorization that involves C need to be joining the summation at that section of the summation. So let's say this has a C in it, this has a C in it. Are there any other C's? No, there isn't. So these two variables involve C. They need to be moved right to the end where C is going to be working on those two particular variables. Then after that, the next thing we're eliminating is a D, so we need the summation of the D. And what involves a D here? Well, this involves a D, so that needs to be on the left side, on the right hand side of the summation, of this summation. And what else has a D? So this one has a D, it needs to be there as well. What else has a D? That's it. Then we're eliminating I, which is the next one. So we eliminate I. All of the things with I's need to be on this rightmost side of the elimination procedure. So there's an I here, there's an I here, the factorizations that have the scope including an I. Then the next one is an H. So here's your H. So all of the H's need to be here on the side of the on the right hand side of the summation. All of the G's need to be on this side, all of the A's need to be on this side, and the L needs to be on this side. And what we've now essentially done, if I have to just take out all of my markings, is we've actually eliminated the variables according to this ordering. But we must make sure that we keep checking to see if we are eliminating in the correct order. So we're starting off with C, and then we're going to D, then we're going to I, then we're eliminating H, then we're eliminating G, then we're eliminating A, then we're eliminating L. Okay, so let's start, right? So so how do we do this? Well, for these factors here, these two factors, we need to actually deal with them now. We need to multiply these factors together, okay, and then we need to sum out the C from the factor that results after the multiplication. So let's see, how do we multiply and marginalize We do this continuously until we reach our j. So we're going to create some new notation. So after we multiply, we're going to call the whatever results of the multiplication, the product factor or the factor product, which is going to be denoted by C, and is it psi? I always get these ones confused. Psi, and then we're also going to introduce the marginalized factor. After we marginalize the psi, we're going to end up with a tau. Okay, so tau is going to be used for just the summation of the after being marginalized. Okay, so let's start. So everything else is exactly like on the previous slide, except I've highlighted now this the part that we're going to multiply. So we're multiplying these two elements together. So we multiply them and we end up with this element. So this here is the multiplication of these two factors. It has a scope, notice, it has a combined scope. Okay, remember when you multiply factors, and I've shown you how to do that previously in a previous lecture, then you actually end up with the joint scope. Then we have to actually sum over them, and I told you that tau will be used to indicate the summation. So we indicate the summation, and we're going to now take all of this out and then put tau 1 in place with the scope of d for this particular factor. So let's see, we've done it. Here it is. Okay, it's on the next slide. Okay, great. So now we need all of the scopes of D on this side. So we have the scope of D here, it's correct, and another scope. If this scope here didn't involve D, we can move it out of the summation, okay? But it does involve D, so it stays here. And we're now going to actually then take this factor, okay, and this factor, multiply them, and what are we going to get? What are we going to get? We're going to get the next C. Okay, and then that next C, we sum over that next C with that particular scope of G, I, and D, because remember you're going to have G, I, and D, which is the combined scope of these two, and you have to then sum over D for this. Okay, so that's where we are now. We're going to sum over D for this particular product, and once we sum over D, we get our tau of the combined scope minus the D. And we continue in this way. So now you're getting it, right? So what is it? Now there's an I here. We've got to make sure that this tau has an I. Indeed it does. If it didn't, we can kick it out. And so we have the I. We then multiply these factors together. We end up with C. And we have an I after that, which then gives us a tau of A and G. The tau of A and G has nothing to do with H. Notice, so this H here has nothing to do with H. So what we do, we then remove this tau from okay, so where was I? So we get this tau because the H doesn't because this H has nothing to do with this AG, we can kick it out of there and bring it here to the back of the summation. Okay, so we do that, we end up with this, and we just then sum out H. We end up with we sum out H and we end up with this, which gives us another tau. We check the scopes. This is a G, this is a G, this is a G, so we can continue. You then multiply all of these factors together and you end up with this guy. You sum out over G, you end up with this. You sum out G. Okay, I might have forgotten to do that. It's fine. Oh, yeah, it is. Okay, so we sum out G, we end up with tau 5. And then after that, we see, well, we need an A here and an A here, so we can do the multiplication. Then you end up with your next psi. Sum out A, you end up with this here, JL, and then finally, you can sum out L, and you end up with tau of L. And then this last factor here will give you the values of J only. So whatever your J was, maybe it was 0.2 and 0.8, that'll be what your J is. All right, so this is the probability of J. Okay, so I hope this makes sense. I hope you get the algorithm, right? I can see it gets a bit confusing. Maybe the only thing confusing about this algorithm is the fact that here you get a combined scope. Maybe that now gives you a combined scope, and this whole idea of the summation over the factor, maybe that's a bit confusing. So wrap your heads around those two ideas. But those ideas are also here, right? So it's the two most important ideas in variable elimination, which is this idea that I told you about. If something doesn't have anything to do with it, you can move it out of the summation. Okay, so this has nothing to do with it, so you can move it out of the summation. And the other idea of doing what we call marginalization, which is just summing out a particular variable. In this case, we're summing out B. Okay, so I think if you can wrap your head around those two ideas, then the algorithm is simple. Don't forget that the elimination ordering also plays a role. So you need to remember that as well. Okay. Right, so we can summarize all of the steps that we just did, and we did quite a lot of steps. Look, this is over multiple slides. 7 over 7, there's probably like a dozen steps here for this one. You can do it much faster because I obviously did this in detail so you can see what's going on, but you could have skipped a few steps. As long as you got the ordering of these nodes, then like here, for example, J and 6 and 6, that's what you need, because you're going to end up summarizing all of this information in a table. So look at this table. So these are the steps of variable elimination. There were 7 steps. It looked like a lot more, but there were only 7 steps. And we eliminated it based on a particular ordering. So the ordering that we chose was C, D, I, H, G, A, L. And if you do it based on that ordering, then you get you get the scope of the factors used. So here to generate in the first one we had, remember, C and D, which was these two. If you go back up right to the top, you'll see them here. Here's it here at the very beginning. We had this. We had those two factors. So when we were marginalizing C, we had those two factors, that those were involved in that procedure, and so we write them down here. We also write down the variables involved, which is this combined scope here. So CDE, which will be CD, GIDD, which is GID, IAIGI, which is GAI, and so on. And then we also write out the new factor that we got after marginalizing. So we have the new factor here, tau, 1, which when we take out C, we end up only with D, and so on. So obviously you can have, depending on the variable how the variables are eliminated, in what order, you will have different tables, right? So for example, here's another table that uses a different variable elimination ordering. So here we had C, D, I, H, G, A, L. Now I got G, I, A, L, H, C, D. Now this is the part of the lecture where I'll ask you, can you see a difference between these two tables? Yes. And then one of you very clever students will raise your hand and say, yes, I see a difference. And the difference I see here is that here we only ever had a very small number of variables involved in the multiplication and the summation. But now look at this. Look at this one. This one has how many variables? 6 variables. 6 variables involved in this very first one, just to eliminate G. Eliminating G takes 6 variables, okay? And eliminating C first only took 2 variables. Is there something here? Yes. So it turns out that, and how much, what will be the size of this table? Suppose everything was binary random variables. The size of this table to sum out that G will be 2 times 2 to the 6 times, so 2 to the power of 6. Okay, so it's a big table. If you had, and this is just with binary random variables, if there were maybe 10, this will be much higher, and so on. So this, it looks like the ordering does matter because it produces different kinds of complexities. The other thing to notice here is that even after summing out the variable, you still have a very big factor. You still got to store that factor and then use that factor in the next multiplication. So that's another thing to notice. Okay, so I hope it's coming across that how the variables are eliminated does play a huge role in what's going on here. Okay. Maybe it's really great that this lecture is online, because in case you're missing some of these ideas, you can rewind and go back. And you can't do that in the lecture necessarily. Right, so how do we deal with evidence? Well, in this variable elimination procedure, it's not really such a big deal, right? Because dealing with evidence is, so before we just calculated the probability of J, but we could also just add more variables in there, and then just calculate the evidence like we did on that second slide of this lecture. So if we have if we have we're calculating the probability of something given some evidence, so here's the probability of J given in high intelligence and low happiness, then we just calculate this joint distribution using variable elimination. So that's the probability of J, I, and H, okay, for those three variables. And then we use this tau that comes out. So the tau will be the J, I, H. We then just we'll have a table called tau like that at the end of our variable elimination algorithm. And from that, we can have the joint distribution of it. Okay, we can calculate we can just eliminate J then to get the evidence from tau, and then just compute this. We can then just compute the probability of J given the evidence, which is from our tau, this value here, or this set of values here, divided by this value here, which is also from our tau once we eliminate. So it'll be, in other words, summing out J for J, I, and H, and then reading off the value from there. So dealing with evidence isn't really a big deal. So variable elimination can deal with evidence very easily. Okay, so as I said, the elimination ordering plays a very important role in the run of variable elimination. So elimination ordering important for variable elimination, and so we find out that for this particular run of variable elimination, we had a specific ordering assigned to it. Okay, so I'd like to introduce you to a concept which helps us to gauge the complexity of the elimination procedure, and this is called the induced graph. And the induced graph is it comes from this table, or this variable elimination run. And what happens is it's denoted as I of the induced graph of G, given the ordering, right? It's an undirected graph over all of the variables in the network. Okay, I don't know why that happens. Over all of the variables in the network, where there's an edge between I and J, if they both appear in the scope specified at each step. Okay, so for example here, C and D will be connected, fully connected, right, between those two variables, and then G, I, and D will be fully connected in the induced graph. G, A, and I will be fully connected in the induced graph. H, G, and J will be fully connected in the induced graph. G, J, L, and A will be fully connected. So there'll be an edge for all of these variables. All four of these variables, there'll be an edge between each and every one of them. In other words, G is connected to J, L, and A. J is connected to G, L, and A. L is connected to G, J, and A. A is connected to G, L, and J. So we do this for all of them, right? And that becomes our induced graph. So I can ask you to draw an induced graph from a run of variable elimination. So notice that the induced graph actually modelizes the edges. Now, I don't know who came up with this word of modelizing edges. It's like if these are all together, then they all must be married. Okay, I don't know who came up with that, but it's very strange and weird. It must be historic. So in other words, it's modelizing edges between the variables involved. And these are not in the original graph. So I'd like to show you what it looks like. So remember I told you that we're modelizing them. So the C and D must have an edge between them. This set of variables must have an edge between them. So that's this edge, and this edge. And then we have this one, which is G, A, and I, which is this edge, and this edge. And then you've got this big one here. I'll just do this last one, which is this edge, this edge, this edge, this edge, this edge, this edge. So this, and there's an edge here as well. So can you see this particular subset of variables, because they appear in this row as all connected, as all together, then they must be modelized. They all must be together. They all must be married, modelized. Okay. And the induced width, the width of an induced graph, is simply the number of nodes in the largest clique. These are called cliques. Okay, so this is the clique, this is a clique, this is a clique, this is a clique. So this is a clique, this is a clique, this is a clique, this is a clique. Oops, this is a clique, this is a clique. Oops, this is a clique, except for letter for those three, and so on. So you look at this, you can look at this variables involved, and then you can find all of the cliques. And what you do is you take the maximal clique, which is this one, and you subtract 1, and that gives you the width of the induced graph. So in other words, there's 1, 2, 3, 4. That's the largest one. So 4 minus 1, which is equal to 3, and that's my width of the induced graph. Okay. All right. So another NP-hard problem. Finding the elimination ordering that provides a minimal induced width is NP-hard. So isn't that depressing? And the reason is because you have to actually then work out the variable elimination and then and try all possible configurations to find out the minimal induced width. And this is the reason why it's NP-hard. So this is not an easy problem to find exact inference or approximate inference in graphical models. But having said that, like I said before, even though these are all just like very scary results, like NP-hard, this is NP-hard, that's NP-hard, we still end up having really good manageable complexities, even for very high dimensional Bayesian networks or Markov networks. So don't be scared off. We still can get really good computational complexity. And this is still a very principled approach to do inference. I mean, as you can imagine, I mean, what would be better than this? To be able to calculate the posterior distribution. Maybe in your master's, you can look at using deep neural networks to help these inference algorithms so that we can still get all of the transparency in these Bayesian networks that the Bayesian networks give us, but maybe better inference procedures. And I have a few students working on that if you're interested in doing that for your masters. Okay. Of course, that's cutting edge research, right? It's very interesting research. And it's cutting edge because we've only started looking at joining these two fields together now, because deep learning wasn't developed enough to do any kind of work on these kinds of problems. But now it can, so we can start leveraging its computational power to help doing inference for graphical models to allow for explainable AI. Right? That's the whole point of this, explainable AI. Okay, so looking at these cliques, we can look at this clique. This is the clique that we identified before. Okay, here's another clique that we've identified before. If we take all of these cliques, I don't know why it does that, but if we take all of these cliques, okay, and if we put them in a graph, we can actually put them together in a clique tree. Okay, so here's C and D, which was that first clique, coherence and difficulty. Okay, and there was another clique here, D, I, and G. Okay, G, I, and D. G, I, and D, okay, which is grade, intelligence, and difficulty. And then we also had G, I, and A, which is this one here. And then we had this very complicated one with 4 variables, which was G, J, A, and L. And then we had this other one, G, H, and J. G, H, and J, this one here. If we take all of those together and put them into a tree and connect them by the variable that connects them in the induced graph, then we get something called a clique tree. So we're connecting them so for example, these two are connected on D because this clique here and this clique here are connected with D. Okay, and I'll show you another one. This one here, okay, that's a more difficult one to look at here. This one here and this one here, it looks like a house. This one here and this one here, so that's this one and this one are connected by G and A because these two are touching here and these two are touching here. Okay, so we can put them together and we call this a clique tree, okay, from the induced graph. Okay, and we deduced this by looking at the cliques. So, okay, right. So as I said before, so this will come in handy later on, right? So you can just put a pin on this, and we're going to look at it later. So let's first talk computational complexity because that's extremely important. So the induced graph and the size of the maximal cliques heavily depend. It's heavily dependent on the elimination ordering. Okay, if you choose a bad elimination ordering, the complexity blows up. If you choose a nice elimination ordering, the complexity is good. How do you choose a good elimination ordering? We already said it's an NP-hard problem, so that's even difficult. Okay, but let's just analyze this from a dry perspective. So the time and space complexity of variable elimination is 2 to the power of OK, where not so OK, where K is the width of the induced graph. Okay, for this particular problem here, the width of the induced graph was caused by this particular clique, and this one here had a size of the induced width was 3 because it was 4 minus 1, and so the complexity of the algorithm we just did upstairs there was 2 to the power of 3. Okay, it doesn't sound so bad. Obviously, it increases with the induced width. But I mean, we come a long way, right? In the first part of this lecture, I told you that the elimination ordering, I told you that in the first part of this lecture, we had no choice but to blow up the table based on how many variables there was in the model. Okay, so in other words, if there was 10 variables in a model, then your complexity had to be 2 to the 10. But now, with variable elimination, it's no longer to the power of all of the variables minus 1. It's now only to the power of the maximal, it's the width of the induced graph, right? That brings it down significantly, because now it's only the most complicated clique. It's now dependent on only the most complicated clique and nothing else. So good orderings will keep the factor sizes small, and bad orderings will yield them unmanageable. Okay, so it's unmanageable for time and space, because you got to store these factors as well, and you got to wait for them to run in, to actually marginalize and do products. So that's where it becomes very difficult. Okay, so variable elimination can also be represented in a different way. So let's look at the way we know for up to this point, and then we'll look at a different way of managing this variable elimination in a more visual way. So we have the very maybe from first principles kind of way that we saw before, and now I'm going to show you a different way. So this is the different way, and this is the way, the old way. Okay, the old way is old as in you just learned it, but now it's old. So we have implemented the variable elimination algorithms. How do we do it? We created a factor psi by multiplying the existing factors. You've seen that before. And the variable is eliminated in psi to generate a new factor tau. And how is it eliminated? It's marginalized. So marginalize. From that, you then have your tau, and you put it back into the algorithm, and then that is multiplied into another factor, and then marginalized, and multiplied into a different factor, and marginalized, until eventually you marginalize the last variable to be eliminated, and you end up with the tau that you want. So you can look at this in a very different way. Okay, and this is called using message passing. And here it's very similar, and the intuition is the same. So we consider the factor psi, and instead of thinking of it as just one step of the process, it's now considered to be a computational data structure. Okay, and I'll show you what I mean by that later on. And these phi's take in messages, and the messages will be this tau. And those tau's are generated by other factors, and it takes these and it generates new messages, tau, and that's used by another psi, and that generates another tau, which is used by another psi, and it goes into a round and roundabout way to be able to do this variable elimination. Okay, so before I can show you an example of that, I first need to show you what is a cluster graph. And this cluster graph is very much essential. It's a data structure that is essential to facilitate this process of message passing. So we need to first discuss this cluster graphs. So what is a cluster graph? It is a cluster graph is an undirected graph. Oh God, indirected. It's an undirected graph, right? That we use to visualize messages. Okay, so we're going to visualize messages, and each node in the cluster graph is a subset of variables. These are the clusters. These can be the cliques that we saw before. Clique 3, like what I showed you before, that actually has, each one can be thought as a cluster of cliques, okay? And that gives you a clique 3. From the previous slide that I showed you, this one here, okay? It's something like this. Where in this case, these were our cliques, okay? But the cluster graph is a more relaxed kind of definition. And the cluster graph, which is, so these clusters, they don't have to be cliques. They can be C of I. They don't have to be maximal cliques. And so each subset of the variables, okay, between each subset of the variables, there's edges. And these edges are what in graphical models, we've got a word called subsets. And these subsets are the common variables between the two clusters. So whatever the common variables are between Ci and Cj, that'll be the subset, and we denote it like this. Okay. So the whole idea behind this is that we have some kind of conversation that happens between clusters. And these clusters, they talk about nodes. So the nodes, which are the clusters, they know about a subset of variables, and they talk about those variables. They talk about it through the subset. Okay, so they like to gossip about the nodes, and eventually they reach some kind of convergence. So let's look at a particular example. So here we have a cluster graph. So this is what I was talking about, a cluster graph. And this is also with the student example. So C is coherence, D is difficulty, and so on and so on. And these are all of the different factors, the size that we were dealing with in our variable elimination algorithm. So this is what a cluster graph actually is. So here's a cluster, here's a cluster. So this is cluster, and this is a cluster. Oops, I'm not sure why that happens, but I hope it's not too distracting. So here's a cluster, and what's in common between these clusters? The D. Okay, so then that's what's going to be connecting them. Here's a cluster, here's another cluster. What's in common between them? The G and the I. Okay, here's the G and the I, here's the G and the I. So we then make an arrow, we put a G and an I here. What's in common between these two? So this is my Ci and Cj. What's in common? That gives me my subset of Ci and Cj. Okay, so what is the difference between the cluster graph that I'm showing you now and the clique tree that I showed you earlier? So let me go back to that clique tree. So this is the clique tree. What is the difference between this and that? Well, if we look at these two things together, which I didn't put them together, but if we look at them together, you'll notice that these two things are not there. These non-maximal cliques, 6 and 7, are not there. Okay. Okay. So we're making really good progress here, right? And now let's relate our run of variable elimination to this clique, to this cluster graph. And if you recall, we eliminated C first, okay? So we started off with C and D, okay? So here's our C and D. If I go right back to the variable elimination, the long way, when we wrote out the kind of proof kind of variable elimination steps, then you'll notice that C and D were the first two factors. They had a scope. The C and D there was a C and D and a C, and we had to eliminate marginalize C from that. Okay, so that was the first step that we did. Okay, then we eliminated C. And so we eliminated C, and we had a thou with a scope of D, which went into the next set of variables, next set of factors, which we multiplied. And then we eliminated D from that. And then we eliminated something else. And then we eliminated something else, and something else, and something else, and something else. And eventually we ended up with our J. At the end of it. Okay, so you can think of variable elimination, what we just did, as going through this very this nicely laid out cluster graph to give us our output of our thou of J. Okay, so it goes through. I wrote little arrows here for you, so you can see how it's moving between these two, between the different clusters. Okay, so this last cluster has a name. It's called a root. This is called a root. And the root, it's called the root because all of the messages are sent to the root. Okay, it's a bit counterintuitive from what roots are in trees, but this is the language we use in graphical models. Okay, so now we define the cluster graph. Very nice. But now there are two properties. When you're creating these cluster graphs, there are two things that you need to remember. The first thing is that there are two properties. Okay, so these are the two things. So thing 1 and thing 2, right? Thing 1 and thing 2. So the first one is called the family preservation property. And all this says is that each cluster needs to be assigned a factor. Each cluster needs to be assigned a factor. And for each factor, there should be an appropriate cluster. For each factor, there should be an appropriate cluster assigned to it. Okay, so we need to do that. And then the second thing we need to do is make sure that the cluster graph has a running intersection property. And the running intersection property simply says that for any factor x, the set of clusters and subsets containing x form a tree. So this sounds very complicated. Let me show you what I mean by it. Okay, let's start with the family preservation. So that's the first thing, right? So in the family preservation, I said that each factor should have an appropriate cluster to be assigned to. And so if this is the joint distribution, these are all of the different factors that I have. These are all of the different factors that I have in my cluster, in the joint distribution. So I'm going to assign this particular cluster C. I'm going to assign this particular cluster CD. So 1 is going to have both of these guys. Then 2 is going to have I, phi of I, and also phi of G, I, and D. Remember, because I've got to have all of the scopes need to match up. So this I is here, it's fine. The C is here, it's fine. The C and D are here, it's fine. Okay. And after that, what's next? So let's go next. This is an AI. Okay, AI and AI is perfect. There's LG, LG, and LG. It works out. Here's JLA, JLA, it works out. HGJ, HGJ, it works out. Oh, and then we're done. Okay, so wonderful. So we managed to get all of our factors. All of our factors are now assigned a cluster. Okay, and for now we have to do the running intersection property. So that's the second one. So if you didn't understand what this text meant on the top here when I was talking about for any factor x, the set of clusters and subsets containing x form a tree, let me explain it to you. So for example, for this subset for C, you only have C here, okay? And because it's one node, it is forming a tree. Okay, here for D, D appears here, here, and here, and this node is connected to this node, which means it's a tree. Okay, I is here, I is here, I is here, and this is a tree. And now G is here, 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 and indeed this is a tree. Remember, tree just means that every node has one parent, right? So here, 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 and here we go. It's a tree. L, so L, 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 here it's a tree. So it would violate the property if there was an L here, okay, because that means that it's not a tree anymore, it's a forest. Because this will have an L here, and it's disconnected from these L's here, and so that wouldn't work. Or it wouldn't work if there was an L here and an L here, because then you're going to have this, which is not a tree. So this is a tree with J, okay. And then H, finally H, oops, finally H is just this one, so that's a tree as well. So well done. Now you know what the running intersection property is. So you can go through my slides. I made them very nice for you. It was a lot of work to make these slides. So use them and to help you visualize. Okay. So previously we showed, so this is the part of the lecture where we normally take a break. So if you want to pause the video and come back after 15 minutes, you can do that. All right, so let's look at now message passing using the sum product. So previously we showed that we can obtain a cluster tree using a run of variable elimination. Okay, I showed you how to do that. So let's now do the reverse. Okay, let's perform variable elimination on a cluster tree. Okay. So I want you to quickly convince yourself that this particular click tree that you saw earlier is indeed a cluster graph. So it needs to satisfy the family preservation and the running intersection. So you can pause the video and then check the definition of the family preservation rule in this click tree and check the running intersection property for the click tree. So just for the family preservation, you can actually do that on yourself. It's easy. So here it is. I've done it for you. So you can assign each of the clusters. So here's one here, 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 and it all fits perfectly. And then the running intersection, oh, I don't have a slide for that, but you can see, let's just take D for example. D appears here, here, and here, and then that's a tree. Okay, if D appeared here, then it's not a tree, and then this would be violated. Okay, because that would have not been connected. Because there would have been a tree here and a tree here, which is a forest, and that's not a tree. Okay, so message passing using the sum product. So you can actually use the click tree that I showed you, okay, to guide your variable elimination process. Okay, we can do more than just guide the elimination process. We can actually perform variable elimination. So the factors psi is computed in these click trees, and messages are sent along the edges, along the subsets. So each click takes in an incoming factor, multiplies them together, sums out whatever needs to be summed out, because remember the subset needs to it's passing it along, and so you can't have variables that are outside the subset inside of the factor when you pass it along. So you need to sum out those nuisance variables and then send the outgoing message to another click. So let's see how we're going to actually do that. If the click C prime requires a message from C, then we must wait for that message. We're not allowed to just continue with the process in exact inference. Okay, and so in approximate inference, we will relax this assumption, but for exact inference, we're not going to do that. So the other really cool about clique trees, the cool thing about them is that they actually can represent multiple runs of variable elimination, not necessarily just for one run. And I'll show you how that works later on. The final really cool thing about variable elimination, I have to talk about this as well, is that it allows for efficient execution because it caches calculations. Okay, so when you compute something, maybe you compute your initial potential, then you don't have to recompute it. It's still there. It's sitting there as part of the data structure's definition. So, when I talk about these things, you might not understand, but let's look at it in a context of an example. So let's do this step by step. So we're using variable elimination with clique trees, and let's use this clique tree that I showed you before as a data structure for variable elimination to calculate the probability of J. So step one, we must first generate all of the initial potentials. Okay, so we need to assign all of the factors from the joint assignment, the joint distribution, from the joint distribution that we saw on the first slide or the second slide, I can't remember, but we're going to assign each of them to this clique tree. So we assign this here, it has the correct scope, it can go in there, this goes here, these two can come to this one, these two can come to this one, and this goes here. So all the scopes are matched up with the clique tree. Then we multiply these guys together and we get this. So we multiply these two together, we get this. This becomes just that. Multiply these two together, you get that. Multiply these two together, you get that. Oh, and then this one just becomes this. So we end up with these. These are called initial potentials. Initial potentials, okay? These are called initial potentials. Step two. So we want to calculate P of J. So we need to pick a J, any of these clusters that have J. So we can pick this one, we can pick this one. So we're going to pick this one, okay, for the sake of the slides. We're going to pick any of the clusters that contain J, and that we need to make that our root. Okay, so in this case, we're going to pick 5 to be our root. We could have picked 4 as well, as I told you. So if 5 is our root, then now we can create directionality to our tree. It wasn't that, see, there was no direction before, but now we can have directionality because now everything needs to point to the root. So we've got an arrow now going this way, going this way, going this way, and going this way. So everyone points to the root. So the next step, which is step 3, is we are ready to now propagate through the clique tree. And we start off with any leaf and then work our way to the root. So we start off with any leaf, right? This is not a leaf. This is not a leaf. This is a leaf. This is a leaf. We can start off by either 1 or we can start off by 4. So we're going to put down our initial potentials from the previous slide, having calculated them, and we're going to start passing messages around. So we start off by the leaf, like we said. We start off through the leaf. Where do I write it here? Any leaf. And we have here, we're going to send a message from 1 to 2, okay? And this message is going to have the subset D, okay? Because we need to have the subset D when passing that message across. And why? Because it has a D on the subset, okay? And for us to do that, I've got to sum out all of the nuisance variables here, and the nuisance variable here is C. So C needs to be summed out, multiplied. So C needs to be summed out from the initial potential that has a scope of C1, and C1 indeed is C and D. Okay, so this is what C1 is equal to. So in other words, we're going to sum out C from this particular scope to get a scope over D, and that scope over D is going to be passed along the edge, and as a message called a delta of 1 to 2D, and that's the message's name. Okay, so we do that, and then we pass it along. So now the next time we're gonna compute the message, it's going to be the old message, which is this one here, the old message, okay, multiplied by the initial potential for the initial potential for the second cluster and its scope. So the scope here is going to be G, I, and D, which is the same scope as before. We multiply these two guys together, and then after that we sum out D. Okay, we sum out D. Why? Because D is not in the subset that's going to be passed across. So we need to get rid of D so that we only have the variables in the subset. And that'll be now my second message, so 2 to 3. We then do that again. So I pass this one across, pass this one across. Now I've got the old message, which is this here, is this one here. Okay. Oops. Okay, is this one here, and then I got the initial potential for this clique, or this cluster. It's better to call it a cluster, even though in this case it is a clique, but it's a cluster graph, so we'll call it a cluster. And from there we have our I, which is the only thing that's not in the subset, and so on. And so we end up with this new message from 3 to 5. Can you see that this message wouldn't have been possible if it was not for this? And this message wouldn't have been possible if it was not for this. So we need to have the preceding messages in order to calculate the next one. And so this now becomes the next message to be passed on. So that's now, so we can't compute this guy. Why can't we compute 5? We can't compute 5 yet because we do not have the last message coming from the side. So we've got to get this message first in order to compute 5. The 5. So let's now go to 4 and compute the message from 4 to 5 using G to Gj, okay, and we're going to sum out over H for the initial potential of the fourth clique, or the fourth cluster, and the scope of the fourth cluster, which is C4. And so we do it, and we end up in our last step. So now we've got all of the messages have passed to the root. So this has passed, this has passed, this has passed, this has passed. So now we are here. We need to now compute the last one, and that's step 4. So the last one is in the root. We want to calculate P of j, and so all we then do is we say we create a new factor. So I've ran out of names here, so let's just call this beta. We can call it tau if you want. I mean, it doesn't matter. And that's going to have a big scope. Okay. It's going to have a big scope because you're taking the initial potential of 5 and you're taking the message from 4 to 5 and the message from 3 to 5. Remember these guys here, this one here and this one here, and you're putting them together, you're multiplying them out, and that gives you now a big scope. Okay, and then finally we need to sum out the nuisance variables because we're only interested in j. So we sum out Ga and L, so we get rid of G, A, and L, and we only left with Z, and we're done. So to make this a bit more clear, we're going to get an unnormalized function. Why? Because of these messages here. It's going to make it unnormalized, and from the unnormalized function, unnormalized potential, it's just going to be the summation, which is this here, of Ga and L, and then the product of these two, which is from here. So this summarizes what I've just shown you. Okay, so sum product message passing algorithm summary. Just to give you a taste of what we've just done. Maybe a summary of what we've just done. So the type of message passing that we did in these previous slides is called the sum product. Okay, we'll look at a different kind of one later on. We'll look at the max sum later on. And this here is it's called the sum product, since the messages from both the clusters is computed as follows. Okay, so number 1, to compute the message, we need to sum over the clique of I minus the subset, because we don't want to get rid of the subset. We need to pass the subset through. The initial potential multiplied by the product of all of the messages that we had previously. Okay, so that's all of the messages previously multiplied by the initial potential. Okay. So in other words, the clique C of I multiplies all the incoming messages, which is this part here, from its neighbors with the initial clique potential, which is this part here, which creates a new factor. And that new factor is our message. Okay, all right. So and we have to obviously sum out, and then we get our message. Okay, so that's great. Once the root receives the message, we calculate the unnormalized potential of all of the factors, okay, by just saying x minus the cluster's scope for the root's initial potential multiplied by all of the message that comes to the root. And if we do that, then we're done. So let's talk about the orderings that we can have. So I told you that we can have different elimination orderings, and each of these orderings affect the actual elimination procedure. So for example, in this particular cluster graph, we could have started here with 1 and then did 2, so that's 1 and then 2, and then we could have done 3, and then we could have started on this leaf 7, 6, and then started on this leaf, then 4 and 5, and then we're done, because then we would have had 3's message, 4's message, and 6's message all into 5, and 5's the root. So we could have had this particular ordering. Alternatively, this cluster graph could have also encoded the ordering 7, which started here, then goes to 6, then goes to 4, then goes to 1, then goes to 2, then 3, then we have all of the messages in order to give to 5. So we could have had different elimination orderings based on the procedure. So here the elimination ordering can be summarized very nicely by using these constraints. So 1 must come before 2, 2 must become before 3, 3 must become before 5, 4 must become before 5, 7 must come before 6, and 6 must come before 5. And we find that there are other orderings, but these are two examples of the orderings that follow this constraint. So the last thing we need to talk about in terms of these trees is the calibration, and we'll talk about this again in the context of the max trees and so on. But calibration is when we actually have an agreement between the different clusters, pushing messages up and the messages coming down. So let's see what we mean by that. So we've learned a hell of a lot about exact inference. In fact, this was a heavy lecture. I can imagine you must be having a headache by now. So maybe you should pause it, get some coffee, and come back. And so this was a heavy lecture on exact inference. But we haven't really addressed one issue, but that's not a big issue. When we have to calculate, so we can calculate this, and we can calculate the evidence of J. But what about when you want to calculate probabilities of variables that are not within the scope of the cluster? So for example, here we've got 4 variables that are not in the scope of the cluster. So let's look at this. Here's an example. Say I want to calculate L, J, and I. Okay, there is no factor here. Oh no, sorry, there's no cluster here that has all of these 3 inside of it. So we can't make that the root. We've got this here, and we've got it here. Okay. So a nice way to do this is then just to do an up run of variable elimination, do a down run of variable elimination, compute the factors from those two, and then multiply them together, compute the factor from here and from here, multiply them together, and then sum out all of the nuisance variables. Okay, so we need a way also of updating this guy, because we did a variable elimination going upwards, remember? Okay, but that means that these ones that were downstream, upstream, they never got all of the benefits and all of the information of the messages that were passed from these guys. Okay, so the intuition is then to also have another run of variable elimination on the cluster graph, one that goes up and then another that goes down, so that all variables, all clusters, not variables, all clusters are updated with these messages. And if we do that, then we can calculate these kinds of things. We can calculate these probabilities. So then we're going to have to calculate the joint probability of each subset of variables in each clique, and then we can use that to be able to calculate these kinds of things. And if we not these kinds of things, all possible combinations, all right? Because then we'll just have to take two updated probabilities from any clusters, multiply them together, marginalize out all the nuisance variables, and ta-da! You would have you would then have a variable. You will have the factor of focus. The factor of focus. Maybe I'll be known for that phrase, factor of focus. Okay. Right. So we're going to do that. Right. Let's do that. So in order to do that, we need this notion of calibration. So the notion of calibration means that it really helps us because we can do an upward pass of messages and then do a downward pass of messages. And if we do that, then we would have calculated the posterior probability of all of those initial potentials using just twice the computational time of one run of variable elimination, which means that we've basically solved this problem for all possible inference that can come from the model by just running the variable elimination twice. So one very important thing I should have made this in red. This should have been in red because you must remember, right, that you always use the initial potentials when you do calculations. Okay, so in going back to this, here, this is the initial potential, initial potential, initial potential. Okay, these are all initial potentials. Even when you're going downwards, when you're propagating backwards, you don't use the updated potential. right? You use then the initial potential again. And the reason why you need to always use the initial potential is because if you don't, you'll be counting the same evidence twice. You'll be double counting evidence, which is not good. So in other words, it's like the variables talking about each other, and then that the information that they shared about the particular variables, the information that the clusters have shared about the particular variables goes around the cluster graph and then comes back to the same cluster, and then the cluster gives the same information that it spread around, which makes it reaffirm its own ideas about the subset. And that's a big problem, right? Because you don't want to be reaffirming your own ideas. You want to rather be unbiased, and then rather just formulate your beliefs about what other people are saying rather than what you are saying. Okay, it's like I'm sure you have a friend like that, a friend who sometimes reaffirms his ideas with his own ideas, and then he becomes more ignorant. This course is very applicable to real life. I think we can even have a course like this for guidance counseling. This idea of the evidence in the way evidential reasoning works in Bayesian networks, and how you can have explaining evidence away in a V structure. All of this is very applicable to real life. Maybe one of you will one day write the guidance counseling handbook of PGMs. Please, I hope I'm entitled to a free copy of that book. Okay, right. Let's now talk about upward pass and downward pass. So we spoke about the upward pass. You're all very clear about it. So that's easy. We have our initial potentials, okay? And you have your variables. This is all cut and paste from the previous slides. And now we done an upward pass all the way to the root, and we are now here. We are at the root, and now we need to do a downward pass. So we start now passing these things back. So now this comes from 4 to 5. So this is the old message that came from this side. We're now passing it down, and the 5 to 3 message is defined by we summing out the nuisance variables which are not in the subset, which is this and this is in the subset, so this must go and this must go. So J and L must go, and then you have multiplying it by the initial potential, not the modified potential of the cluster scope, multiplied by the old message that came from 4. So you do that, and then you do the same thing going backwards and backwards, and then the other way. And now once you've done this, congratulations, you can now calculate the posterior probability over any combination of variables in this network. So you can calculate the probability of J, you can calculate the probability of C and G given H and J. You can calculate the probability of C and G given J0. You can calculate the probability of G and I and something that's not in this one, and D. You can do anything. You can do any kind of computation. Congratulations. Right. So there's some beautiful properties that we get. So when the algorithm terminates, remember I wrote P tilde of the factor. I wrote that sometime before. When you get that, that means that this is an unnormalized probability. So you need to normalize it to be able to use it. Okay, and you're looking. Okay. So if you're looking for a specific probability, like here. Let's say we're looking for the something within the same cluster. We're looking for the probability of G. Then, if you made this the root, you still have to eliminate I and A in order to get this probability. So probability of G, I, and A. You eliminate I and A, and then you end up with P of G. Okay. So you need to eliminate all of the redundant variables in the clique. And if you're going to be going across cliques, then you need to multiply them and then marginalized out the variables that don't matter. So the great thing about calibration is that it doesn't matter which clique you select, okay? Because both cliques, all the cliques, if they're talking about variables, they must agree on their marginals. They must agree on the marginals. And we call this calibration when they agree on the marginals. So all adjacent cliques have the same modified potential. Okay, so in other words, the sum of the cluster minus the subset for a particular initial potential and given its scope is equal to the adjacent cluster's initial potential marginalized over the cluster's cluster scope minus the subset. So this is so important because that means that everybody's talking about the same thing. It's not like everybody has different opinions about each cluster. Each cluster, we all have the same kind of opinions about them. Okay, so I hope you're not getting too tired because we're almost done. We're going to do kind of the same ideas for approximate inference. So I would have had a separate lecture for approximate inference, but unfortunately I have to do this in 10 lectures. So I've taken the most important parts of approximate inference and put it together in this lecture of exact inference and approximate inference. And let's talk about what is approximate inference. So approximate inference is very much the same thing, except now we talk about an absolute error. So we're trying to calculate the probability of some kind of event, but within some kind of epsilon error. And in some cases, this is appropriate. In some cases, it's not. So in the problem statement here, for example, calculating the probability of a rare disease sometimes can be 0.00001, and you might not be able to find an epsilon which is acceptable because you won't know how to calculate. You won't know how many zeros there's going to be here, so you can't define an epsilon. So you can't say that I want to know that disease with an error of probability 0.9 because there's just simply no way of this is such a noisy value. You're not gonna be able to identify it. So you need to take consideration of that and have rather a relative error. But my point of this slide is just to show you that approximate inference is something that we can think about, and it's something that we can do. And it turns out that we can also do it in a very principled way. As I told you before, approximate inference is NP-hard. And we're going to use the variable elimination procedure in approximate inference as well. So the difference here between the approximate inference stuff that I'm going to show you now and the variable elimination stuff with exact inference that I've shown you previously is just that the exact inference procedures are produced in click trees, while the approximate inference procedures are performed on cluster graphs. Okay, so the exact inference, you've got a tree. If you go back to the slides here, you saw those were all trees, and now we're going to be talking about cluster graphs, which can sometimes look like this. They're connected, they have loops. Okay, and if we look at the misconception network, which is the one where you had your friends that are talking to each other and didn't include. So the independence assumptions, I'm sure you remember this from the lectures, is that A is independent of C given D and B, and of course D is independent of B given D is independent of given A and C. If we add these two independence assumptions, we have them nicely in here, and we can have each of the subsets we can have a particular cluster as A and B, which is this one here. You can have A and D, which is this one here. You can have B and C, which is this one here. And you can have D and C, B and C, which is this one here. And then obviously the shared variable between these two clusters becomes the subset. So A and A becomes A, D and D becomes D, and C becomes C, and then these two become B. So you have this beautiful cluster graph with a loop, which gives you a nice way to do approximate inference. It gives you a data structure to do approximate inference. So this is not a click tree, okay? I'm sure you figured that out by now. And it contains loops and cycles, so that's what makes it not a tree. And this is why we call it loopy approximate or loopy belief, because it is having these loops. And kind of the same procedure, right? We actually initialize the cluster graphs with our initial click potentials. So we've done that here. We have initial click potential, initial click potential, initial click potential, initial click potential. We've got the subsets indicated here by the circles. Okay, and if I just take out all of my noisy markings, then we can also have a message that you can pick a random place. Now, before I said you must do it as you must start off at a leaf. Now here you can start off anywhere. So you start off anywhere, and you have the message going to be. It can just be 1. It doesn't have to be anything complicated. And then that's passed to A, B, and then there you compute the new message from 1 to 4, and that's the initial click potential multiplied by the old message, summing out over all of the variables minus the subset, which becomes a B, and that goes to the next one, and then that goes to the next one, and that goes to the next one, and then finally you do the backwards, the other, and you continue in this way until you converge. And that's basically it. And that's how you do approximate inference. So it's the same kind of thing, but this time we have a different kind of calibration. It is a weaker calibration because now every adjacent set of clusters agree on the marginal of their variables. So they only agree on that. And that is weaker because in tree calibration from the previous slide, the adjacent clusters agreed on all the variables they had in common, not just the subset. Okay, so this is the difference between approximate inference using graphs, clique graphs, and using cluster trees, okay, the clique trees. So there is a big difference, right? Here we had agreement on all variables they had in common, not just the subset, and then here it's only on the subset. Great, so that's really nice. And what's nice also is that there's convergence. Okay, so networks with potentials that are closer to deterministic are more likely to have problems with convergence, and there are examples of that. But what's nice about this is that we get some of the really great properties of exact inference, which is that the marginals agree for some subset of variables, and we can do it relatively cheaply with passing messages around. And obviously this is a cheaper way of doing inference because we have relaxed properties, okay, but it's a cheaper way of doing exact inference, which also follows the variable elimination procedure, which makes it very, very suitable for high dimensional networks, such as Markov networks, where I told you where each of the nodes represent something about the superpixels of the image or whatever else. Okay, great. So this is pretty cool. I'm now going to move to a different problem. So we're done now with approximate inference using and exact inference using variable elimination. I'm going to show you, this is related to variable elimination, but it's a different problem. In the very beginning, I'll go right back. I can't go back. Okay, I can't go back. I don't know how it's not working. But if I click on the problem statement part here on the side, then you will go right to the beginning where I spoke about two ways of doing inference. There was the map inference, or maybe I spoke about it in a different lecture, but there was map inference and there was probabilistic inference. But map inference is a different problem. And in this problem, we want to find out what is the maximal, the most likely outcome. Okay, and why would we need to know what the most likely outcome is? Okay, it turns out you can find if you can find out what's the most likely thing to happen in your Bayesian network, then you can use it for noise reduction, source separation, for images. You can use it for segmentation and restoration. You can use it for channel decoding in robotics, localization in mapping. You can use it for planning in robotics, in genetics. You can do linkage analysis, and you can do it for speech recognition, anomaly detection. There's lots and lots. I've written a whole lot here. Lots of stuff that you can use map at inference for. So this is calculating the most likely assignment. So maybe the most likely assignment maybe is this. Okay. So this is the most likely thing to happen. This event has the highest probability. And let's see why is this a difficult problem? So let's say we've got this Bayesian network, right? So you got this part here. So you got this Bayesian network, okay? If I select the most likely event for this particular variable, it'll be 0.6, okay? So that's for blue. The color blue is most likely. And if I calculate the most likely event here for this variable here, if I look at where blue is, when I'm given the evidence of blue, okay, and I calculate the most likely event. So if it's blue, it's either going to be this guy or this guy, and it's 0.5. So I'm going to select 0.5, and it turns out that this here is not appropriate because it really didn't capture the highest. So picking the highest values per variable doesn't really tell me about the map assignment. So highest variables per variable doesn't tell me anything about the map assignment. Okay, all right. Okay, so you get that, right? So that's a problem. The other issue is it doesn't tell me the highest map assignment, because if I had to multiply these two factors together, so color and shape, to give me the joint distribution, I found that the most likely assignment is not with blue at all. It turned out to be with 0.36 for red, and it to be S, which is what is S? A square. Okay, so the red squares are the most likely things to happen. And there was no way for me to know that from just looking at the individual factors for the Bayesian network. So that's my point. Okay. So finding a single coherent joint assignment, we call it A of star, with the highest probability is NP-hard. That's another NP-hard problem. Most of the problems in artificial intelligence are NP-hard. And finding an assignment X such that the probability of that particular assignment is higher than some threshold probability is also NP-hard. So another very difficult problem. So for the test, I'm sure in your past paper, you saw I actually asked you to do a run of variable elimination. Okay, but in the test for 2023, I'm going to actually ask you this question. I'm going to ask you to do a run of variable elimination with respect to the maxed sum, which I'm going to show you how to do now. Okay, so it's a different kind of question, and I have to ask these variety of questions. So study this one more than variable elimination from the previous slide. When I say more than variable elimination, obviously everything we spoke about in this lecture is variable elimination. Okay, but I'm specifically talking about if I have to go right back here. In the test, I asked you to do this here, to do this run of variable elimination. Okay, so to do these steps, 2, 3, so on. But that is the past test. But in this test for 2023, I'm going to ask you to do this here, which is the maximization. Okay, so this, how do you do it? Okay, so let's see. So in order to calculate the most likely outcome, which is the map assignment, you can remember that it is all represented as a product of factors in a Bayesian network. And the product of factors, I then can actually find the argmax, which is the most likely thing to happen for this product of factors. We can represent each of these factors as the log probability, and if we do that, then the multiplication between these factors become a summation. Okay, that's just the rules of logs. And if we do that, then I can represent each log parameter as an actual parameter that I can just, so these are all just factors, but are now represented as log parameters. And if we do it this way, it makes things a lot easier. It makes things computationally easier, because we can then say to find the argmax, the most likely outcome of the probability A, okay, we can simply then just say, we can have the max of L, the max of G, the max of I, the max of D, and we can still have a elimination ordering. So I'm going to just, the elimination ordering associated here is D, okay. I'm first eliminating D, then I'm eliminating I, then I'm eliminating G, then I'm eliminating L. See, I'm first eliminating D, then I'm eliminating I, then I'm eliminating G, then I'm eliminating L. Okay, so this is exactly the same as variable elimination, but this time the context has changed to map inference. You can tell I'm tired already. So just hang in there, we're almost done. We're almost done. I think there's 2 or 3 slides left. Okay, so and this is important because this is in your test, right? So let's try to get through this. And if I look at the P of A, right? I'm not eliminating A. Okay, so we're going to end up with A at the end. Okay, so we're going to maximize now. So we're going to say what is the so this is from our joint distribution. We then group variables. We're eliminating D first, remember, first D, then I, then G, then L. So we're eliminating D first, so we need to group all of the factors that have something to do with D, and we do that. So which one of these have something to do with D? This one here. It's only this one. Oh, and it's this one here. So you multiply those two together and you end up with this product. Then you need to max out D. Okay, so how do you max out D? You max out D by maximization. I'll show you how to do that on the next slide. And there you find in the max of this particular factor, and that gives you now lambda 1, where we maxed out D. Before we summed out D, now we're maxing out D. Okay, and now the next one to go is I, so we group out all of the I's, so there's quite a lot of them. Okay, so all of these guys involve I. We max out I. Okay, then you end up with lambda GA. And then now we got to do G, so these two both have to do with G, so we max out G, and we end up with lambda 3 AL. And finally, you max out L, which gives you lambda of 4. lambda 4, which is A. So this gives us a very nice way of doing maximization, and this looks exactly like variable elimination. Only thing is now we don't have products, we have summations, and we don't have marginalization, we've got maximization. So let's talk about what is factor summation in this context. The factor summation is very simple. It just says that if I've got two factors, factor 1 and factor 2, then all I'm doing is I'm saying if I'm going to be summing them together, I want to create the summation of these two factors. I group them based on this. So A1, B1, B1, C1 becomes A1, B1, C1, which is then just this number plus this number. And that gives me 3 plus 4, which is 7. Okay, let's do another one. So A2, B1, and we've got B1 here, so it needs to be a B1 as well. So B1, C1, or it could have been B1, C1 or B1, C2. Let's pick this one here. So that becomes A2, B1, C2, which is this one here. A2, B1, C2, and that becomes minus 1 plus 1.5, which is 0.5. Okay, so the idea is to then, a good easy way to do this is to simply draw the resulting table as a combination of all of the inputs, okay, and then go through them one by one. So for example, here, if you're calculating this row, then it'll be A1, B2, C1. So A1, B2 is this guy, and B2, C1 is this guy, and so there you know what to sum. It's 0 plus 0.2. Right, how does maximization work? Remember, there were two things. There was this idea of summation, and there was this idea of maximization. Okay, so I realized that I might have said product before. It's not product, it's summation. Okay, so then the summation, the maximization is easy. So if you're maximizing, then you have maximization. So here in the context of variable elimination, there was summing over x. Now we're not summing over x, we're maximizing over x, and so that's why we have this max here. So after you do your summation, you end up with something like this, which is your potential, and you maximizing over b. So in other words, we're getting rid of b. So you have a and c. There needs to be only a and c in the new factor, and b needs to be gone. So what do? We're gonna actually maximize across it. So to get this one here, we need to maximize over two cells in our initial, which is A1, C1. A1 and C1 are here, and A1 and C1 are here. So we need to max over these two guys. So we find the maximum, and the max is 7. So that's what gives us the 7. Then we can, for the next one, be maxing over A1 and C2, which are these two guys, and that's what gives us the maximum 4.5. And then we're maxing over A2, C1, which are these two guys, and that's what gives us 3. And then finally you're maxing over these two guys, which is going to give us the next 3. And so that's how we do maximization in a factor. So to summarize all of this, it's the same thing. So it's now it's called max sum, and the sum of variable elimination and the sum of max sum is two different kinds of sums. The one is summing out, which is marginalization, and in this case it's summing out as in a factor actual operation, which involves adding the numbers across factors, not necessarily summing them out in an individual factor, which was marginalization. So we have consider the extended student network again. We do an upward pass just like before. We do a downward pass to reach convergence. So before we add fees of D and C and so on. Now we've got these. These are our initial potentials, and we then just put them in exactly as we did before. We calculate the messages exactly as we did before, maximizing instead of summing. And this was a product before. Now it's actually a summation. So it becomes about maximization and summation. So otherwise, it's very much identical. Okay, so what do we do? Well, if the map assignment is unique, okay, then there will always be a single maximizing assignment at each click, okay? But if it is not unique, then all we need to do is just add a little tiny random noise to every single factor. Maybe add like a small little thing that just changes it a few decimal places down the line. That will make every factor unique. It'll make the map assignment unique. And if you do that, then you can just use the map sum as I've shown it to you. So this is what most people do if the map is not unique. We add a small tiny noise and it gives us a unique assignment. So in summary, you must be very tired, and so am I, but in summary, we have inferencing graphical models. We can do them, and we can also do map assignments. Okay. The crazy thing about these algorithms are they are all NP hard. Okay. However, we still use them because this is a worst case scenario, and these worst case scenarios often never occur. And just by a few heuristics, we can keep our algorithms that I've presented to you here very manageable. By using an induced width, just reducing the number of dependencies and so on, you can really make inference manageable. And these are very much worst case scenarios. So NP hardness is never a problem really in practice. So exact inference and approximate inference, as you've seen, are very much rooted in variable elimination. They are very much. This is a key thing. Variable elimination is the most important thing in inference for graphical models. And all of the big inference procedures, and there's one that's called junction tree. The junction tree algorithm. And the junction tree algorithm is exactly variable elimination. Okay, it just creates junction trees, which is a clique tree, and it does variable elimination over the clique tree. So variable elimination can be used for sum product and max sum. So this is to calculate map inferences, and the sum product, which is calculating probabilistic inferences. All right, we can also do map inference with evidence. All right, so I'm sure you can imagine how that's done. It's exactly the same as probabilistic inference with evidence, but with the sum in the map and the sum operations. Elimination orderings do affect computational complexity. Here for the map inference, we used a different elimination ordering. If you had to use another elimination ordering here, instead of DIGL, you would have ended up with a different kind of computational complexity. And that does matter. And finally, the important things about approximate inference and exact inference are very much about how messages propagate, how they calibrate, and how they converge. So in exact inference, we just need to do an upward pass and a downward pass. Approximate inference, we need to just try these operations until we see convergence. And and that's basically it on inference. Well,